we're going to talk about how to check the percentage of steel in beams. What is the minimum and maximum percentage of steel that is required to be in beams? Okay. Looking at the diagram here on the right side, this is the one that we saw. I just draw a line. That this is the one that we saw last lecture. And last lecture I didn't draw these, which are the reduction factors, but we'll talk about these later. Now we want to focus on something what we call compression control, transition control, and tension control, right? In the tension control, we said our design should be somewhere in this area for beams and slab because they are tensile, so that the strain should be more than 0.005. Okay, so our rho should be here. If it is in transition, the code allows me to go only up to ET equals to 0.004, which is this point here. More than that is not allowed by the ACI code, and compression controls are for columns, shear walls, and so on. So if my beam design falls somewhere here or here, then it's not acceptable by ACI code. Right. So why do we do that? Because if it is in transition, first of all, if the beam design falls in one of these two, one or two, first of all, the design is not economical because I'm filling the beam with much steel, and second thing, it is not ductile, right? So the ACI specifies something called AS minimum, which is the minimum percentage of steel. AS minimum is actually what? It's actually 3 radical FC prime all over Fy multiplied by BWD, which is the width of the beam and the depth. This term should be greater than or equal than 200 BWD over Fy. If this term is less than 200 BWD over Fy, then we'll choose this. We'll come to see in the applications, right? This is in the US customary. And why do we need this? To avoid sudden failure. We don't want sudden failure in the beam. If the beam has steel that is really less than the minimum requirement of steel, that means the beam doesn't really have steel reinforcement. It's as if it's only concrete. The steel that we put is less than the minimum. So as if the beam doesn't have any steel. It's so less that as if it doesn't have any steel. So what does that mean? The beam is acting like a concrete plane without a steel, and it will suddenly fail without any, it is brittle. It will suddenly fail without any deflection, and it's not ductile. Okay, so from this, actually we know that rho minimum, or rho, this is minimum, is actually AS minimum, or over BD, right? If you substitute this here, then rho minimum will be only 3 radical FC prime over Fy. That means it's a property dependent. It's a property dependent, material property dependent, doesn't depend on the section. It's just depending on FC prime and Fy. Okay, so we get that, it's important. Actually, what do we mean by sudden failure? If we recall in the first lecture, we talked about something called the cracking moment, right? That means the cracking moment is greater than M. This is what sudden failure means. If I didn't put steel or I put less than the minimum, this is what will happen. And this will cause a brittle material and a sudden failure. Okay, anyway. So let's talk about now going back to this diagram. So how do we get these values? You see over D, coefficient, and so on. So what's written here, and it's 0.037. How do I check where is my steel percentage? When I design, am I falling in the compression or tension or transition zone? So to check that, now guys, let's see how to check that. See, to check the rho max, let's start with the rho max. And rho max actually falls here. This represents rho maximum. And I mean represent when the strain is 0.05 and C over D is 0.375. So how did we get that? So if we say rho max, right, we all know from here, we all know that if I draw the strain diagram, or the strain, yes, from here the concrete reaches its crushing strain is at 0.003, This is the strain in concrete, 0.003, at a distance called small c. And this distance, we said it's called d minus c because the whole distance is d. And this reaches, the strain in steel reaches 0.005, which is this here, number here, right? So what does that mean? If we do similar triangles, basic math, c small over 0.003 equals to d minus c over 0.005. And by this, you will get c equals to 0.375d, or c over d is 0.375, which is this one. What does that mean? That means 37.5% of the section is controlled by c, which is the compression. So 37.5 of the section is compression, and the rest is tension. Okay, so we all know that the small c, which this is the small c actually, is a over beta, right? And a is what? Okay, a is what? A is ASFY, or we can substitute AS with rho BD. Rho BD Fy divided by 0.85 Fc prime B. Cancel B with B, you will get A. So C is rho, in this case rho is the rho maximum, because we are using this strain 0.05, multiplied by D, multiplied by Fy, divided by beta 0.85 Fc prime. So C substituted, which is equal to 0.375D, right, from here. Cancel D with D, so eventually you will get the equation of rho max. Rho max is what? 0.375 multiplied by 0.85 multiplied by beta, which is actually 0.85, multiplied by Fc prime divided by Fy. So it's a material property. So whenever I face a problem, I want to check my steel, I will just check what is rho max. First, where am I in rho max? What's the limit? Okay, so let's go back. Let's check now how to calculate the other one, which is rho balanced. Rho balanced is here. This is called rho balanced. Okay, rho balanced will be rho balanced is same thing. We have to draw the strain diagram or the stresses here, right? And then we will say this is the crush 0.003 in concrete, but the strain is 0.002. It's just a yielding 0.003. This is C, this is D minus C in distance, right? Similar triangles, C over 0.003 equals to D minus C over 0.002. You will get C is 0.6D. That means 60%. That's why it is rho balanced. That's why it is compression controlled. 60% of the section is controlled by compression. Okay, so what does that mean? Doing the same math, C equal A over beta. We know what's A. I don't want to repeat it. So it's equals to rho balanced D Fy divided by 0.85 beta Fy equals to 0.6D. Cancel D with D. So eventually rho balance is what? 0.6 multiplied by 0.85 multiplied by beta Fc prime divided all by Fy. So now we can check. We got rho max. We know how to calculate rho balance, and we are set to do the calculation. Okay, so let's take two example applications on this. We have two beams. We will choose Fc prime for both of them the same. So Fc prime is 4000 psi, and Fy is 60,000. This will be for both of them. Right, so determine the design moment capacity. So what's phi mn? Now, starting with the steel, no, rho is what? AS, we have AS and we have BD. So let's see, where am I? Which is at 4 divided by 15 multiplied by 24. This gives me 0.00111. Okay, so let's check first before even continuing and computing phi mn design moment. Let me check if this beam is ductile, compression zone, transition zone, tension. Let's see. So first, let's compute rho max. We know that rho max from the, just I wrote it in the previous slides, 0.375 multiplied by 0.85 multiplied by beta, which is 0.85 multiplied by fc prime 4,000 divided by 60,000, which is the fy, and this will gives me 0.0 0.0181, which is more than rho, right? Which is greater than rho. So we are indeed somewhere in the tension zone, right? To check, so that's the line here. That's compression zone, that's tension zone, and this is the transition, right? Here is the rho max. If I already got my value somewhere here, which is less than the rho max, so I'm away from the compression, but I don't want it to be way less than rho max, so it is less than the minimum, right? Because it can't be less than the minimum, otherwise we will have sudden failure, as I said. So let's compute rho minimum. Rho minimum is what? Rho minimum is, from the slides, previous slides, free radical fc prime over fy, that it should be greater than or equal than 200 divided by fy. If you do the math quickly, you will get 0.00316 greater than or equal than 0.0033. You'll choose the bigger of these two, so it's this one. So it is even, so rho is greater than rho minimum. So we are in tension. So the beam is ductile and we're in tension zone, which is the desirable zone. So quickly, just calculate phi mn is what? Phi, which is 0.9, or let me write it, phi ASFY times D minus A over 2. A, calculated from the equation, we know that A is what? ASFY again, divided by 0.85 fc prime B, right? If you do the math, it is 4.71 inch. Plug it in this equation, so phi mn will be 0.9 multiplied by ASFY, which is times 4 times 60, D minus A over 2, right? And then divide the whole thing by 12, so you will get it in feet. Oops. Right? Finally, phi mn is what? 389.6 k-foot. Great. That's great. Okay. Going to the next example. Next example, we will let's compute also the same thing. So we determine phi mn. That's the question. Same fc prime, same fy. So let's start computing the steel, as over bd, and we will, it's 4.68 divided by 12 multiplied by 15, and this will give me 0.026. Since we're using the same material, I mean same fc prime and same fy, then we will have the same rho max and rho minimum, right? Because they are material dependent. They're only depending on fc prime and fy. Now, in which zone we are? Rho is even bigger than rho max and way bigger than rho max. So we are either in the compression zone, we're either here, or we are in the transition zone, right? So let's compute the row balance. Row balance is the compression zone, is the limit for the compression zone. What's row balance? Row balance is 0.6 multiplied by beta, multiplied by 0.85, multiplied by fc prime, divided by fy. And this will give me row balance is 0.0206. 0.0206. It's even greater than row balance, guys. That means this section is compression controlled. And I mean by that, it is good for columns, not for beams. So it's rejected by ACI code. All right, this is what I want to reach. Hope you guys enjoyed the video, and thank you so for watching.